By the classical treatment of the specific heat of solid, we confirmed the Dulong-Petit rule, saying that the specific heat per particle is given by 3 kb. Hence, from the treatment, we conclude that the specific heat is independent of temperature. Yet experiments clearly show there is a temperature dependence and the specific heat drops to zero for T approaching zero. The reason for this discrepancy is that the classical treatment fails and we have to resort to a quantum mechanical treatment. Again, we resort to our earlier description that the solid is described by masses which are attached to each other by springs, meaning that each particle in the solid can be described by an harmonic oscillator. For the harmonic oscillator, the states are characterized by energy levels Ek, which were equidistant with respect to each other. The energy of the different states, K, is thereby given by K plus 1/2 h bar omega, where omega is the eigenfrequency of the system. Now the solid is made up of n particles, and each particle is described by 3 harmonic oscillators in the x, y, and z directions. Now the partition function of a single harmonic oscillator in the quantum mechanical view is given by z1 of beta is equal to the sum of all states. In this case, it's the state k from 0 to infinity, e to the minus beta k plus 1/2 h bar omega. Taking out the constant factor e to the minus beta h bar omega half for each of the terms of this infinite sum, we see that the sum is nothing else like the geometric sum for which we know the result. Now, using on top the definitions of the hyperbolic sign, we obtain a very compact equation for the single harmonic oscillator partition function z1 of beta given by 1 divided by 2 sine hyperbolic beta h bar omega half. Now the total solid is made up of 3n of those oscillators, hence the n particle partition function zn of beta is given by 1 divided by 2 to the power 3n times the n factorial times the sine hyperbolic of beta h bar omega half to the power minus 3n. The partition function now lets us calculate the mean energy of the system and also the specific heat we are interested in. The mean energy is given by minus the log of the partition function with respect to beta, giving a term of 1 divided by sine hyperbolic from taking the derivative of the logarithm times the internal derivative of the sine hyperbolic gives a cosine hyperbolic, and the internal derivative of the arguments of this hyperbolic h bar omega half, and multiplied by 3n. The result is again simplified using the definition of the hyperbolic cotangent. From there we obtain the specific heat per particle Cv, which is equal to Cv divided by n, which is given by 1 divided by n, partial derivative of the mean energy with respect to beta, and the partial derivative of beta with respect to t, giving a fairly simple equation which contains omega squared divided by cosine hyperbolic of beta h bar omega and a prefactor kbt squared coming from the partial derivative of beta with respect to t. From our quantum mechanical description, we thus obtain the specific heat of a solid is dependent on temperature. What should be expected from our result is that at high temperatures, our solution should approach the Dulong-Petit rule, and for low temperatures, we should expect a drop-off of the specific heat towards zero. Let's first consider the high temperature case. High temperature means beta is much smaller than 1, for which the cosine hyperbolic of x can be approximated by 1 plus x squared divided by 2. Now, using this expression in our result, we obtain that the specific heat per particle is given by 3 kb, confirming the classical result and showing the Dulong-Petit law. For the low temperature case, where beta is much larger than 1, the cosine hyperbolic of x can be approximated by e to the power x, leading to the expression for the specific heat, which is now getting proportional to t to the minus Te divided by T, where Te is the Einstein temperature h bar omega divided by Kb. This result tells us that the specific heat should drop off exponentially with temperature. The experimental results follow the description of the Einstein Solid. Yet at very low temperatures, we see a deviation, typically around 20 Kelvin. This deviation is due to our summation on the energy scale up to infinity. Yet for a real crystal, the wavelength is limited to the distance between the particles and hence also a limit in the maximum frequency allowed for the summation. This has been realized by Debye, leading to the Debye theory of solid that you will learn about in solid-state physics. You should realize by the example we discussed today of the specific heat of solids, the strength of statistical physics has been recognized and ultimately seen as important as the theory of quantum mechanics being developed at the same time.